Hello and welcome to today's video. So this is my power controller, well, my preliminary schematic for the power controller. I need 4 of these on my Solectria E10, so that warrants laying out a board for it. And so here's the schematic. So of course it's preliminary, so a lot of these pinouts will change. I haven't done the layout yet, so I usually just move things around when I get close. You know, when you're doing layout and it's like, oh, that wire gets close to that pin, okay, I'll just move these around to make it work. But we're using the Part35 EV256 GM106. This is the same microcontroller, 5-volt microcontroller that I used on the Nissan Leaf BMS replacement board. Exact same one, 64-pin QFN. We got some blinky lights. Everybody likes blinky lights. So I got one that for power, air, transmit, receive, pre-charge, and contactors enabled. Those are subject to change. They're software controlled, so they're not actually hooked to anything. They just go over the micro, so you can make them do whatever you want. I got, of course, the transceiver for CAN bus here. Well, actually, it's a translator. The microcontroller actually does all the CAN stuff. Threw an I2C expansion port on here because, could always do some I2C expansion. We got current sense conditioning circuit here, just a voltage follower with a little low pass filter set to 482 Hertz there. And you can see VREF, I'll show you that in a second. You can flip it to whatever you want. It's an adjustable supply. We have a current or a temperature sensor here. This is used to measure the temperature of the pre-charge resistor. Don't want to turn on if it's getting too hot, so we can shut it down if something's wrong. This is the VREF for the current sensor, and you can see you can change out this resistor here to do 5-volt or 8-volt. I'll be using the I'm not planning on using the current sense that comes with Nissan Leaf. I'm going to use a different one. And so that one requires anything between 6 and 12 volts. So I'll be running at 8. So I also have it to where I can turn it on and off, because it does burn up about 20 milliamps. So I can shut it down when you're in low power mode. We don't need to measure the current. Power coming in, we got CAN bus. We go through a 3-amp fuse. We got a reverse protection diode. Some capacitors, and then a 5-volt regulator, good old 78 MO8 or 78 MO5. It's good for 500 milliamps. Should be enough to power everything. And then, of course, the programming connector, which is just a 6-pin header. And and ID. Because I'm going to have 4 of these boards, I need a way to index them with different CAN IDs, and this gives me the ability to have up to 16 of them. Yeah, it's overkill, but, you can see that goes over there. But, yeah, I only need 4, so I could get away with 2 IDs, but then there'll be somebody that wants to add a 5th or a 6th, and then that just makes it easier to build it all in. And, yeah, that's pretty much what's going on this page. The next page is where it gets more interesting. So there's a lot of stuff going on here. So go ahead and zoom into here. So the whole point of the this power controller board is to be able to turn on the contactor and do pre-charging and measure the input and output voltages. So you can see here I've got my 150 volt A, 150 volt B side, and so this one side would be connected to the battery pack, the other side would be connected to the main system bus. And because I have 4 of these in parallel, we want to make sure that we can disconnect and connect the battery packs if there's an issue with them. Excuse me, I'm still kind of sick. So you can see we've got a whole bunch of 39K resistors. There are actually 10 of them in series here. And then with the 10K, and this gives me a 40-to-1 voltage sense. So essentially, it's dividing the stack voltage by 40, and I happen to have 40 cells, so if the average voltage is 3.75 volts on a cell, then we'll see 150 volts. Well, 150 volts will be equivalent to 3.75 volts per cell, and that can be read by the micro, 0 to 5 volts. So we do that on both sides. And I'm not 100% sure. I'll go through all this, but I may not actually populate all of them, just because if this is the side that goes to the battery pack, I can get this data from, I can get the pack voltage from the BMS, and then the other side, I'll have 4 identical ones, so when they're all connected together, so I may only populate one. I don't know yet. It's going to be a lot of components. You'll see that here in a second. For the pre-charge, we have a 50 ohm, 50 watt resistor, and Milo just jumped in my lap. Hello, Milo. How you doing? Yeah, well, you're kind of, I'm in the middle of recording a video, and you're kind of in my way now, because you keep bumping me. If he can chill out, then you can stay. But anyways, so we have a 50 ohm. Milo, you are being super annoying. Okay, 50 ohm, 50 watt power resistor. It actually looks like this one, since Milo has interrupted me here. It looks like that. Quit nuzzling the camera. Yes. Okay, so essentially, this is the contactor. And Milo, you are just... Milo, can you hop down? Yeah, I know. Oh, and you got like flea medication on you too, don't you? Why don't you hop down for a sec? Go on. There you go. Okay, sorry about that. Back. Well, anyways, this is the pre-charge resistor. It's a 50 ohm, 50 watt resistor. You can't actually do 50 watts out of them, but it can do a few hundred watts, probably about 500 or so watts for momentary, and that's what we're using it for. It's just for pre-charging. So anyways, that's this guy right here, and we've got 2 IGBTs, one on each side with the built-in diode, and these ones are really nice. These TLP 191Bs are essentially solar cells with an infrared LED, and so we can enable the pre-charge. I'll turn on this guy and this guy. That'll allow current to flow through here. That shines light on the solar cell, which develops a voltage and actually turns the gate on. But you can use these to turn on IGBTs and MOSFETs. Not so much on transistors, or on like a bipolar transistor, because you don't get very much current. But they get up to about 10 volts or so. And then there's like a 1 meg resistor in here to bleed them off. But they're really slow, but that's okay. We don't care. They're just going to pre-charge. We're going to run some current through here. So if we've got 0 volts over here, 150 volts over here. Turn these guys on. We'll run through this resistor. And then when that voltage, we can sense both sides. We can measure right here and here. And when we get those close to equal, then we turn this guy on, and we put a high here, turns this guy on, which turns this guy on, and that allows 12 volts to go through our contactor and clicks it in, and that's of course this guy right here. So that should work really well. And then, so that's what that's doing. The problem is we've got 150 volts, 160, 170. It can actually be up to 170 if I charge to 4.2 volts. I'm not going to charge that high, but you know, worst case. And so we got this high voltage here. We don't want to expose our microcontroller to the high voltage. We want to keep everything isolated. You can see that these are isolated. So this is going to the micro, the 5 volt, but it's isolated, and these are like 3000 volts isolation. The contactor, of course, is isolated, so this can be, so we're keeping all the high voltage over here, except we have the potential, like if this opens up or something goes bad here, we can get high voltage leaking across. So that brings us to these two circuits. So look at this one here. They're both identical. And essentially what we're doing is we're creating an isolated voltage sense. And so we've got the voltages coming in here. It goes through this op amp, and that is generating through here, this 200 ohm resistor. We are actually outputting a current, essentially. So if you were to look, let's see, yeah. So we've got current coming through here, goes like this, and it's part of the feedback loop. And that causes current to flow through this guy to ground. So essentially, light from this LED shines on these two photo transistors, or photodiodes, and that causes a feedback loop to form here. And with this resistor, we end up with a proportional amount of light based on 0 to 5 volts in over here. And that light, because it's in this feedback loop, is maintained, proportional to how much voltage is over here. And this other side, we create the same thing. So see how this 5 volts comes through here, and then it generates a voltage here. We do the same thing. 5 volts comes across here. Current will flow through here due to the photoelectric effect, and we develop a voltage across this 39K, which gets amplified, and we create a voltage follower, and we get an output here. This goes to the microcontroller. So all what that means is that if I have 1 volt over here, it gets converted to light, and then I get 1 volt over here. If I have 2 volts over here, I get 2 volts over here. If I have 5 volts over here, I get 5 volts over here. So that allows an isolated analog voltage sense, so that we don't have to worry about the 150 volts being exposed to the 12 volt system. So we can still maintain isolation there. Now, unfortunately, this little guy needs power for it to work, because we need at least 20 milliamps or so to run this LED. And so we can't. There's not an easy way to actually generate that, other than I've got one of these little tiny transformers in here to 1 to 1.3, and we'll essentially use the microcontroller PWM both of these guys at about 117 kilohertz, and that will cause my 12 volts to go through here. We half wave rectify it. We end up with about 8 volts over here. We run that through a linear regulator with these little, I think it's like a 100 milliamp job, and we end up with 5 volts, literally just to power this guy. But it's isolated again, so this is good at 3600 volts, and this is like good at 3600 volts. So we're maintaining our isolation between the high voltage and the low voltage side, and the other side's identical. It's exactly the same circuit. So, like I said, I might not populate, because I can get all of this data from, like I get the voltage from the BMS, and they have a whole bunch of little isolated chips already in there that they're using to measure. Well, they're actually powered by the batteries, the cells themselves, but that's isolated 12 volt system. So I can actually get all of this data, so that means I don't need all of this, and that means I don't need all of this, which is going to cost a lot. So that allows me to essentially save on all of that. The output size, I really only need 1, because the common bus will be tied to all of them. I might maybe populate the front battery box, might have 1, and then the rear battery box might have 1, just for redundancy. But other than that, I don't know. I don't really need 1 on each, but it's there. It'll make the circuit look nice and symmetric. So essentially, all of that's going to go here. So my goal is, so this is the contactor I'll be using. It's from the Nissan Leaf battery pack. This is their current sensor. It's just kind of unwieldy. You can't really use it, like, it just kind of doesn't fit anywhere. It's kind of really designed for their battery pack. But what I'm planning on doing is, imagine this is a battery terminal or a connector, like a cable coming in, and you put the nut on it, right? So that holds it on there. You do the same thing the other side, and then I'm thinking the board just kind of is this cutout shape, and it'll just slide over the top of the 2 nuts. So if you've got your bus bar or your cable coming in, you put the nut on, put the other nut on, going through it. So all the high current is through that connection. Then on top of it, you slide this power controller board on, and then you get another nut, because these are pretty tall. I think you can fit a lot on there. And then, so if you imagine a circuit board coming out over here, and then that ends up with this guy sitting on there, pre-charge resistor. So, there's a lot of room on here. This would be your 50 ohm, 50 watt, even though this is a 15K. I will have 50 ohm, 50 watt resistor, and that'll just bolt onto the board. A little current sense, do that voltage divider with the resistors. Oh, if you don't know, the reason you do the resistors here like this is to minimize the amount of voltage that each one would see. So if I fire up a calculator here, you can kind of see. We'll do this branch right here, right? So we've got, say, 150 volts. Well, let's do worst case. So we got 4.2 volts times 40 cells, 168 volts, right? And now we're going to divide that by this whole stack, which is 400 kilo ohms. So we divide that by down. We're talking like really small current here. So store that away. So if we go with this 39K resistor, we only have 16.38 volts dropped across this resistor, which is well within its capabilities. I think they can do a lot more than that, but we're gonna go with 16.38 volts across each one, worst case. So that works out really well. And for those that are complaining that, oh, you have all these resistors hooked up to the battery pack all the time, it's going to drain it. Well, I've got 65 amp hour battery, right? And if I divide that by my current for one leg, it's 154,000 hours. And if I divide that, what do we got? 24 hours in a day and 365 days in a year. So we're looking at, it'll take 17.66 years to discharge the battery. So if your truck's sitting for 17 years, then it's got other problems. So I'm not worried about like putting a MOSFET or transistor down here and turning this leg on or off. I think that's be totally fine. There's other things that will drain it much quicker than that. But anyways, that's why I have all these resistors in series. It's just to get the individual voltages across each one much lower, so we don't arc across any of them. And yeah, so I don't remember what I was saying before. Oh, yeah, I'm not going to be using their current sense. I'm actually going to be using this guy here. This is a 225 amp current sense. He can fit like a 1 gauge cable through there, maybe even an aught cable. Single aught. Now, unfortunately, these things run 6 to 12 volts, so I'm going to plan on powering it with 8 volts, and then I can just put this, rather than having to use this weird funky shaped one here, I can, put this anywhere along the input or the output cable, and it just can hang out on the, right where it plugs in. So I think that would be a lot easier. And I'm going to make a little board that goes on here that'll condition it, because this will, this is ratiometric, so at 8 volts, it'll put out, I think it goes 2 volts, so the output is centered at 4 volts, so half of 8. So if I power it with 8 volts, centered at 4 volts, and then full scale is down 2 volts, and then full scale positive is up 2 volts, so this will only actually put out 2 to 6 volts full scale. So I'm going to make a little circuit board on there. I'll do some conditioning and translate that over to 0 to 5 volt, which is what my microcontroller is expecting. And then, so that way full scale will be 2.5 volts out of this will be 0 amps. 225 amps will be pretty close to 5 volts, and minus 225 amps would be really close to 0 volts. So that's the goal anyway. But yeah, this video has been super long, but hope it was educational. Thanks for watching. Bye. Hopefully I can get it all to fit a little circuit board that'll fit on here. It just bolts right into the contactor. And then this just plugs right into the to the board, and it controls it and does everything. It'd be really cool. Just have a little connector here for CAN bus and 12 volts and ground, and it'll be self-contained. Build up 4 of them. Should be good. I mean, this thing's pretty big. There's a lot of room. And then I need to find some. Yeah, this is kind of interesting. The Nissan Leaf, they use these to mount them, but these brass inserts are supposed to have grommets in them, like elastomeric, rubber grommets that you put the screw through to hold them so that it's vibration isolated. And they don't do that. They just have a really wide, flat top screw bolt with a very thin. It's like this size. It's really odd. These things can actually float around a lot, but yeah, I plan on actually putting the correct rubber piece in there when I mount it. So yeah. Anyways, yeah, I got long. Anyways, thanks for watching. Bye.